So today we are going to look at machine learning training, aspect of machine learning. So we spent the whole of last week talking about the history, having an understanding of what machine learning is, what's the difference between AI and ML, and all of that. This week, we are going to dive into the nitty-gritty. And like I said earlier, I want to warn everyone there will be a bit of mathematics in today's class, even though I will do my best to make this maths as easy as possible for everyone to follow. So don't be afraid of maths. It's not scary. I know that we all have this general idea that maths is scary, but that's because of how we were taught. So it's not hard. Okay, so we will start by looking at how you set up your machine learning environment. We have a few tools that we will use, but we'll start with the Jupyter Notebook, which I introduced last week. So right now, if you have your laptop, you should kind of set it up. If you haven't set it up already, if you are sitting where your laptop is within reach, I would advise you to grab it and you can follow along. The Jupyter Notebook installation is not a very difficult thing. So I'm not going to spend the time in this class to show us that, but I'll send us the materials or the links for you to install it locally. Remember, I also said that when you are using Google Colab, you already have Jupyter Notebook. So you can create a new Jupyter Notebook simply by typing colab.new. Just like everything else, sheets.new will give you a new Google Sheets. Docs.new will give you a new Google Doc. Slides.new will give you a new Google Slide. So Colab.new will also, or Forms.new will also give you a new Google Form. So Colab.new will give you a new Jupyter Notebook that is saved in your Google Drive, right? So you can see that happens. So we will do a lot of exercises today using this. So it's good to set that up already. And the good news is that if you have a Copilot, like I do, you can also have a bit of AI support that will auto-generate code or auto-complete code for you. So we'll look at some of the tools that we have and how you can set up your machine learning environment. We also have Google Colab, which I've mentioned. Then we have Kaggle. Kaggle also has a notebook, a Jupyter notebook. All of these are basically the same thing. And the code that you write in one, you can transfer to the other, or the notebooks that you prepare locally on your machine, you can run it. You can run it with VS Code. You can also upload it to Google Colab, to your Google Drive, and run it on Google Colab. You can also upload it to Kaggle and you run it as a Kaggle notebook. So it's all the same thing. Then we'll look at data processing pipelines. So data processing or pre-processing is a very big area. It's a very big area, but as it is now, we don't even have enough time to look into that. But I'm going to try to give us a little bit of background behind it so that we can at least start, doing some things. But one of the best tools right now for you to use for data pre-processing is Pandas. Of course, sklearn also gives us access to data pre-processing, what they call pipeline, which we'll look at later on in the training, in the course of the training. But today we will do a bit of Pandas using data frames and what Pandas allows us to do. Then after that, we're going to do linear regression with one variable. Linear regression is the very basic of machine learning. And why it's very interesting and very useful is that it ties back to our basic maths that we did, in school. When you study maths in school, we had this thing we call, line of best fit and all of that. You had all of these things we call a equation of a straight line, y equals mx plus c and all of that. So we start from linear regression with one variable so you can understand how machine learning came from this thing that, most of us study in school and we didn't even bother to understand what is it for, why are we even doing it, right? But that's where machine learning starts, right? And even when we talk of neural networks, a neural network, even though it's a construct that is mimicking the human brain in terms of how it's designed, but a neural network eventually can be broken down into a linear equation. A single neural network is a single linear equation. So by the time you take millions of neural networks and put them together, you're essentially solving a million simultaneous equations. That's what you're doing. Well, it's not all simultaneous. Maybe some of them are multivariable, simultaneous, simultaneous equations. Some of them are yeah. So it's a combination of different things. I don't even know if there's anybody who has done a mathematical representation of a layer in a neural network or all of these billion parameter models that we have. So you find that at the end of the day, at the beginning of everything is a linear equation, y equals mx plus c. This is the fundamental, the foundation of machine learning. All of the tools that you are talking about, apart from search-based kind of methods or algorithms, but most of them will be on that. So we have linear regression, one variable. We're going to do then linear regression with multiple variables. In other words, multiple y's, multiple y equals mx plus c's. Then we're going to do polynomial regression, which you are going to use multiple x's equals to a single y. And then we'll do logistic regression. So in logistic regression, like I said before, um, logistic regression is kind of classification. You are now using a logistic function. So you are doing regression, but you are trying to decide between one or two things, right? And then we'll look at how all of these things come into play. We'll talk about loss functions, metrics for measuring performance of these models, the mean square error, the cross entropy error, accuracy, and all of that. Then we also will talk about things like gradient descent and how you do optimization with gradient descent. So this now become more complex ways of achieving the same thing. Then we'll talk about regularization, just an introduction to regularization. What is regularization and why are we doing that? So for today, we will run all the way to linear regression with one variable. We're going to go through additional things, including what does training even mean when you say you are training a model? I know there was a lot of questions about that last week, but what does it even mean, right? So we will understand that. Okay. So first of all, like I have already mentioned, the tools that we'll be using will be Jupyter Notebook. So I've already shown you how that looks like. That Google Colab is basically using a Jupyter Notebook. But the interesting thing is that Google Colab also allows us to have access to CPUs, GPUs, and TPUs. These are computes that Google provides. Some of them are free for based on certain limited usage and limited rules that you have to follow. But if you go beyond that limit, then you have to start paying for it, right? So the beauty of the Google Colab, like I said, Google Colab is basically a Jupyter notebook that's in your Google Drive and runs. So there's auto saving, whatever changes you make are auto save, just like everything else on Google. On Google, everything is auto save. If you're making changes to a slide or a document, you don't need to remember to save. Then it has what we call runtime, right? Where you can change the runtime and you can switch to a GPU type if it is available. Then Kaggle, I mentioned that already. So Kaggle also allows you to have some access to free GPUs and some data sets. Kaggle is really known for data sets. So you can pull data sets from, Kaggle for almost anything, for almost any kind of machine learning problem. In fact, Kaggle started off as just data sets and it drew a lot of crowd, a big community, and then they started adding other things to it. So they've added notebooks now and they've added code and all of that. So they've even added, testing framework that allows you to test yourself. So we have competitions on Kaggle for all kinds of things. So Kaggle is a good place to go. Once we started doing some stuff, we'll be pulling data in from Kaggle in order to see how well we do. Then Hugging Face allows us to easily host and share our models or the applications we will build with the model. So you do a model. If you're not a front end or back end, or you're not even a software developer, but you are an ML engineer, you have built some models and you want people to try it out, Hugging Face Space allows you to do that very easily. The way you do it is you can build forms that users can, type in the input or something, then you send the input, you connect those inputs to your models after passing it through a pre-processing pipeline. And then after that, the model will do inference and output comes up. You also post-process this output that comes from your model, and then you can send it back to the user either as a chart or a graphic or whatever. So if it's a classification task, for example, you have the images that will come at the output, and then you send it in there. So Hugging Face makes it really easy for you to showcase your models, so you can interact with them. You can share them with friends who can interact with them as well. Then we have local and custom setup you can do locally on your laptop. So you can use Conda or VM. This is where you are not using a Jupyter notebook. Maybe you're using straight up Python, and you're installing all your dependencies, and you are using VS Code, for example, and you just set it up. So this is also possible. So these are some of the cases where you'll be able to set up. It's not really difficult. So we can run that maybe as a sidebar. For those who don't already have it set up, I can give you directions, or I'll send you a link to direction that you can follow to set it up. And I will encourage everyone to set it up after this class, before the next class. Ensure that you set up at least a Jupyter notebook locally, but of course the Google Colab is there as well to help. So now we talk about the tools. So some of the tools that we will use, right, for setting up, for our machine learning training. I'm going to just mention three. The first one is Pandas, like I've already said. Pandas is an open source Python library and is widely used in machine learning and data science for data manipulation and analysis, right? So it gives a very powerful, flexible data structures, what we call series and data frames, right? So a data frame is a very powerful data structure. In fact, think of a data frame as an Excel sheet, right? But you don't see it visually, but you manipulate it with code. So a pandas data frame is basically an Excel sheet, not an Excel workbook or an Excel sheet or a Google sheet, a single sheet that contains rows and columns. That's what a data frame is. And you can manipulate those rows and columns. You can select stuff. You can change, you can play around, with data. You can do all kinds of stuff. That is what a pandas data frame is. And the things you can do with pandas and how it becomes useful for you in how it becomes useful for you in machine learning is you can basically use it to load various files, CSV format, Excel, SQL databases, and other kinds of data in other kinds of formats. And then you can export those you can import in these formats. First of all, you can process the data, do training on it, do all kinds of things, and then you can export it, right? As well to those formats. So Pandas data frame is very, very powerful. The other thing it allows you to do, Pandas as a framework, as a tool, it allows you to do cleaning and pre-processing of data. So most of the time, you have to do machine learning. Before you do machine learning training, you have to do data cleaning. A lot of data that you're going to, get is not going to be very clean, nice data like that, right? It's going to be data that has a lot of gaps. It has a lot of rough, all kinds of things. So you have to clean it. So Pandas really helps with cleaning data. And some of the things it allows you to do is it allows you to handle missing data. So maybe you have data that collects age and date of birth and things like that, and you can identify those ones. You can use sane defaults, what we call sane defaults. Basically, if maybe you have information and you have missing data in some places, you can say, okay, for the ones that are missing, maybe I can use the value of 0, or I can use the average value from, all of the other values that I have. So you can come up with some, um, smart way, but Pandas helps you. But one thing we have to understand is that in doing this, right, Pandas helps you, but you still have to think about it. You are the one that has to, Pandas doesn't think for you in terms of how you do the data replacement or data cleaning, or how you handle missing data. You still have to come up with your strategy. The only thing that Pandas does for you is to help you implement that strategy once you have decided. So for example, you can decide, okay, where age is missing, I will replace with 0, or I'll replace with average age. That decision is yours based on your knowledge of the data and based on what you want to do with the data. But Pandas cannot do that for you. What Pandas does for you is to, allow you to do it easily, right? So it allows you to identify missing values, what we call nans or null, and then you can then either remove them, replace them, and so on. The other thing that Pandas does is data transformation. So converting data types. For example, if you have dates in your data stream, you want to handle those dates as dates, not as a string. So Pandas can allow you to convert from one data type to the other. So you can convert a string to a date. You can convert a string to numbers, whether it's floating point or integer or whatever. You can use Pandas to convert integers to floating point and vice versa. And then the other thing you can do is to handle what we call categorical variables. So these are variables that are in buckets or in categories. For example, male, female, for example, old, young, for example, anything that is classification, colors, red, blue, green, anything that is classification, what we call categorical variables. So it allows you to convert those categories from words or strings into what we call category labels, which could be numbers like integers, 0, 1 category. The first category, like red, can be given a 0, blue can be given a 1, green can be given a 2, and so on, right? The other thing is what we call one hot, so if you have categories, you can generate a binary equivalent where only one of those categories has the value 1, the rest will have zeros. So those are all things that we can do. And we are going to look at data transformation a bit when we go to when we really want to train complicated kind of networks for complicated tasks. There's feature scaling and all of that. Pandas also helps you to remove duplicates and helps you to identify and eliminate rows that have duplicate values. So the other things that Pandas can do for you is data exploration and analysis, right? So it enables efficient exploration of data sets. You can do statistics on the data. So remember, Pandas is handling a huge amount of data that comes in rows and columns. You can do summaries, you can do mean, median, standard deviation, and so on. You can filter and subset, select specific rows that you want to do stuff on, you want to, do calculations or do transformations. And you can do that based on what we call mask, right? A mask is basically a condition that you can use to select a subset of the pandas data frame, whether it is a row or a column or a combination of rows and columns or multiple rows and multiple columns. The other thing that pandas does is what we call grouping and aggregation. So grouping and aggregation is where you can group by a particular condition or a particular feature, and then you can aggregate based on that grouping. So a good example would be if you were taking, data, you had data that came in a data frame, and we're going to touch a bit of this, shortly. Even though because of time, I will not be able to go into much detail. But let's assume that you had data from coming in from maybe students in a school, right? and you have data on their age, their gender, the class that they belong to, their best subject, and all that kind of stuff. Then you now want to find out the highest, the maybe the total number of, let's say, males, females, right? You want to calculate the score of all females and the total score of all males, right? You would do a grouping. So you group by gender. So when you group by gender, it will give you the gender, whatever values you have in the gender column. So females, males, and so on. Then you have to aggregate. So aggregate is, I choose a column that based on that grouping, I want to aggregate the values on that column. So let's assume you choose a column that contains the score that they have in a particular exam or a particular course, let's say English. So you group by gender, then you aggregate by sum of scores in the English, the column that contains English scores, right? So you can also decide that instead of summing, which is one way of aggregating, another way of aggregating is I want to get the average score. That's also another aggregation. Then you even have statistical, um, you know, um, measures that you can use. So you can say, okay, mean, median, mode. You can say mean, median, mode. You can say, other things. You can say the count. You can even say standard deviation and all of that variance. So each of those is a kind of aggregate, how you get the aggregate. I'll do a bit of examples on this. Then feature engineering is where you can create new features from an existing feature just by modifying an existing feature a little bit. Then Pandas allows you to integrate with other libraries, um, you know, such as NumPy. So Pandas is built on top of NumPy. We'll talk about NumPy next. You can also, it also integrates with Matplotlib. So you can also plot charts and graphs. And then Seaborn for data visualization, scikit-learn or scikit-learn, which is the third library we are going to look at for building and training models. So that is pandas. The next one is NumPy. NumPy is a library used for numerical computation. That's basically what NumPy means. NumPy means numerical Python. So it is a foundational fundamental library in Python that is used for numerical computing. It is optimized for numerical computing. So it can compute really fast, large amounts of data, right? And this is very, very key in machine learning. In fact, you cannot do anything without NumPy these days, even though there are a bunch of libraries that effectively try to build their own, but NumPy is so great that it is basically the best. It's awesome when it comes to, what we call n-dimensional computations. And that's what, it's really good at. It has a basic construct or data structure that we call an ND array. An ND array is an n-dimensional array. That's what it means. So n means it can be any number. So you can use it to represent this, a one-dimensional array, two-dimensional array, a five-dimensional array. So remember last week I mentioned matrices, vectors, matrices, and tensors. And I told you that a vector is a one-dimensional array. A scalar is a zero-dimensional array. A scalar is a single value. It doesn't have any dimension, right? It's just a single value. This is scalar, by the way, in programming parlance, not scalar as per scalar in physics. So you have a scalar, a zero-dimensional object, right? A vector is one-dimensional. It's a single. Then you have a matrix is two-dimensional because it has rows and columns, right? And then a tensor is three-dimensional and on. Actually, all of these are tensors. A tensor is a generic name for any n-dimensional object. So you use NumPy to do all of these. You can represent them, and then you can do really solid mathematical operations with them. Then some of the advantages or key features of NumPy. One, efficient data storage. you can actually store a lot of data. And it stores it efficiently. So it's very fast to store and very fast to retrieve and very fast to manipulate, right? Um, so, and these are all very, very key things that you need in machine learning, because machine learning is really all about manipulating huge amounts of data, right? So if you don't have a library that can do it very fast, it will take a long time for you to achieve anything. So that's one of the things that NumPy brings. NumPy is also a foundation for most other libraries. Like I already mentioned, Pandas is built on top of NumPy. Skippy is science Python. So it's basically a scientific library for Python. Matplotlib is for plotting graphs. Then scikit-learn is ScienceKit for learning. So this is a machine learning toolkit in Python. TensorFlow is we mentioned it already. TensorFlow is built on top of NumPy as well. TensorFlow is like one of the first, the earliest machine learning libraries that could really do heavy lifting when it comes to neural networks and so on. Then PyTorch followed TensorFlow. PyTorch, both are open source now. PyTorch is like now the most often used in the world today, is really favored for research because it's easier to understand and grasp than TensorFlow. TensorFlow uses a graph approach, but Python uses a more Pythonic, what they call Pythonic approach, which we'll see. So all of these are built upon NumPy, and they rely on this n-dimensional array object to get the optimized performance. Then NumPy is also really good with mathematical operations, so you can do almost anything, including the array operations, linear algebra, like we talked about, matrix multiplication, dot product, cross product, inverse, transpose, all of those things, even eigenvectors, eigenvalues, and all of those things are very powerful. If you have ever tried doing the inverse of a matrix, you know it's not easy to do it by hand manually, but NumPy does it without blinking. Fourier transforms, random number generation, these are all part of what NumPy can do, and these are all very, very fundamental for machine learning, training and algorithms, right? Including neural networks, they support vector machines and the statistical models, the Bayesian statistical models, and so on. So the other things that NumPy is really good at doing is what we call vectorization and broadcasting. So vectorization is a situation where you 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 pack all your data in a particular data structure called a vector, and then you do a single thing to that vector, and it gets done to all of those, right? I'll go through this and show some examples. Maybe before we start, I'm looking at the time. Then broadcasting is a situation where you have data maybe in one dimension and you want to spread it across the second dimension. So these are also very, very important operations that are needed for machine learning. So you have the beauty with vectorization is that you can do operations on multiple data without having to loop through them. That's what vectorization is all done at once. It's like parallel kind of operation. And these are also kind of integrated into the various GPUs, TPUs, and other kinds of compute systems that make it to, they make these operations very, very efficient. So yeah, like I said, broadcasting enables operation between arrays of different shapes, making your code simpler and reducing memory usage. Memory efficiency is the other thing with NumPy. It's very, very efficient. It's definitely more efficient than Python lists. Python lists are the most inefficient way of doing any kind of mathematical calculation. They're only good with ordinary straightforward programming. But when you're dealing with large numerical data sets, right? The NumPy ND array is the best, right? So it helps us to do things faster. So that's basically what NumPy is. If you look at this drawing, I want to explain to you. So you have this one-dimensional array. You can see this is what we call a vector. it is one dimensional because if you look at the shape, there's what we call shape when we are talking about ND arrays or generally tensors in any of these machine learning, um, you know, um, frameworks, right? A shape is basically a measure of the dimensions and how many cells you have in each dimension. So for example, this one has a shape that is, it has a single dimension, right? And that dimension has a shape of 4. This 4 here means there are 4 cells, right? And there are 4 values. The 4 values are 7, 2, 9, 10. It has a single axis and the axis is axis 0, right? And it's a one-dimensional array. Now, this is example of a two-dimensional array. It's two-dimensional because you have these two axes. You have the x-axis and the y-axis. Here, you only have one axis. Y-axis, right? And so you have axis 0 and you have axis 1. Those are the two axes. That's why it is two-dimensional. And it has a shape of 2 and 3 because there are two numbers here. The two numbers here correspond to the two dimensions. The first dimension has 2 elements. In other words, you have 2 rows, right? That's the first dimension. The second dimension has 3 elements. That is 3 columns. So this is a 2 by 3. 2 rows, 3 columns. Two-dimensional shape is 2, 3. So this is a 2D, this is a matrix, basically. Now, this is a cube. And you can see it's a 3-dimensional array. It has axis 0, axis 1, and axis 2. So it has a shape of 4, 3, 2. In the first axis, it has 4 elements. That is 1, 2, 3, 4, which you can consider as a depth of 4, right? But this is axis 0. So remember, axis 0 is always captured first when you're looking at the shape. Axis 1 is captured second. So this one, axis 0 is 2, axis 1 is 3 elements. Here you have axis 0 is 1, 2, 3, 4. So it has 4 elements. That's why you have 4. Axis 1 has 1, 2, 3. So that's why it has 3. And then axis 2 has 1, 2. So that's 4, 3, 2. And this forms a shape that looks like a cube. We call it a tensor, right? And then you could have a 4-dimensional array. That's where the problem begins because now we have exhausted the 3 dimensions that human beings are capable of visualizing. If we now want to do a 4th dimension, we'll have to do 3 dimension and then put a second 3 dimension and a third 3 dimension. And at that point, the space is no more space efficient. So you can have multi-dimensional arrays, 4 dimensions, 5 dimensions, 6 dimensions, and so on. The third framework is scikit-learn. Scikit-learn is for training pipeline. Basically, it speeds up training. That's why it's called scikit-learn, scientific kit for learning. Sometimes they just call it sklearn. The SK is scikit, scientific kit for learning. So it's a widely used open source library for machine learning, right? It's just similar to the likes of TensorFlow, PyTorch, and so on. But it's not as powerful as those. It can't lift as much as those other ones, right? So it's also built on top of the other libraries like NumPy, right? And SkyPy, which is a scientific library for technical computing, right? In Python. Then it also is built on Matplotlib. We are going to try using scikit-learn a little bit this week just to have a hang of it. Now, some of the characteristics and features of scikit-learn is it has a comprehensive collection of algorithms for machine learning. It's so good. Sometimes with scikit-learn, it's easy for you to forget all of those principles and how difficult it is to train. You can do linear regression with 2 lines of code. That's how good it is. So it has all of those algorithms. It's all there. So you just use it and you train, right? So a can do various tasks. Classification, so you have algorithms for classification, like support vector machines, decision trees, random forest, k-nearest neighbor, logistic regression. We are going to touch all of this, right? So that we understand the principles behind it. But like I said, after understanding the maths, it's good to understand the maths. You can then use scikit-learn and just write 3 or 4 lines of code and it does it for you. Of course, that's because you want to do bigger things, right? You don't want to spend your whole brain. It's just like, we started off with using pen and paper as babies to calculate 1 plus 1, right? And then we moved on to doing more comprehensive mathematics, still writing it on paper. And then after that, we have what we call 4-figure table or logbook, where you can check values of sine and cosine and so on. After that, we moved on to calculators, where you just type the number and press sign, and it gives you the cosine, tangent, and square root and all of that. You don't need, or logs. You don't need log table or 4-figure table. From calculators, we move to computers, where you write the code and you program it. So you don't even need to be punching numbers. You just load the number in. And so this is how, as you get better in something, you don't need to worry about having to do it manually anymore because you are moving on to bigger things. So in the same way, in this class, we're actually going to look at some of these things, the support vector machines, how it works, decision trees, random forest, k-nearest neighbors, logistic regression, and all of that. But later on, you can just write 1 or 2 lines of code and scikit-learn, sklearn does it for you, right? So classification, regression, with linear regression, with ridge regression, lasso regression, all of the different regression, gradient boosting, which you can use if you do what they call random trees or decision trees with gradient boosting, right? So there are different algorithms all in there. Clustering with k-means clustering, with dbScan, with agglomerative clustering for grouping similar data points. We will talk about some of them, and then we will try the same thing with scikit-learn. Dimensionality reduction techniques with PCA, principal component analysis, LDA, linear discriminant analysis, for reducing the number of features in a data set so that it's easy to either visualize or just work with. So this is what scikit-learn does, right? And I'm not going to jump into scikit-learn immediately because people will not appreciate the magic that's going on behind. Some of the other features, it has a consistent API. So the API is consistent. What we mean by API is an application programming interface. So that's basically what you you what you type, the function signature, how it looks like, and the arguments or parameter list that you pass it is consistent across whatever algorithm you are using. So once you have learned that signature, it's easy for you to use for any kind of algorithm. So it's easy to learn and to use, right? And it allows you to interchange different models without changing too much of your code. The other thing it does is data preprocessing as well. So just like pandas, you can do a bit of data preprocessing. In fact, scikit-learn gives us what we call pipeline. So a pipeline allows you to stack different stages of data processing and then stack it into the machine learning algorithm itself, right? So that you don't even need to worry about losing data, right? So things like scaling, normalization, standardization, like we talked about last week, handling missing values, like pandas can do that. Scikit-learn also allows you to do that. And probably, maybe it might even be using pandas under the hood to do all of that. Then model selection, it allows you to split data into training and testing sets. It allows you to do cross-validation. It allows you to do hyperparameter tuning. And even that matter of, using grid search and all of that, it allows you to do that really easily. Then it does model evaluation. So it trains the model, right? And it allows you to evaluate the model. So you can assess its performance. So things like PCA, accuracy, precision, recall, F1 score, right? Mean squared error, and all the other kinds of errors, cross entropy, and so on. It does it very easily for you. Then efficiency and integration. So with NumPy's efficient array operation, scikit-learn is able to achieve good performance. It basically builds on top of NumPy. It also integrates with the other ones, pandas, like I said, for data manipulation and so on. It has a huge open source community and support. It benefits from large active community. So there's always continuous improvement, and it's readily available and it's free. So that's a quick look at the libraries that we have. I talked about a lot of things here. So hopefully I'll get some time to show us some of these things. And, you know, as we are going on, we'll learn some of these things. So when we talk about support vector, k-nearest neighbor, and all of that. But what I want to start off with first is let's go into machine learning, training your model, right? We need to understand that process. So last week I talked about the stages of machine learning, the model development. We start with data collection, then we did data preparation and pre-processing, then model training, which is what we'll do today, and then model evaluation, and then model deployment, and then model maintenance and retraining. Today, I'll touch a little bit on data preparation and pre-processing, and then we'll do model training, the general process of training the model. And then we'll pick linear regression, and we'll do a manual step-by-step through linear regression with a single variable so that we can understand how that works. Okay, so let's just go into that. So yeah, like I said, data pre-processing, we talked about it last week. I'm not going to go through all of this, but you use it, you handle missing values, encoding categorical data, feature scaling, removing outliers, feature selection extraction. I've said that already. So data cleaning is the process of identifying and correcting errors or inconsistencies in a data set to improve its quality. So raw data sets will often contain a lot of inconsistencies. You want to clean them, right? You want to eliminate irrelevant columns. You want to ensure you have data consistency. You want to resolve missing values through replacement or filling. You want to remove duplicate records, and you want to correct invalid entries and outliers, and then normalize and standardize. So pandas is one of the tools, like I mentioned. The second tool being scikit-learn. So these are some of the functions that pandas will give you. We have a function we call dropna. Dropna allows you to drop rows that have missing values. Dropna basically means drop with some specified value of your choice. Like I said, you are the one that decides the strategy of how you want to fill missing values, right? Panda just helps you do it. Duplicated tells you which rows have duplicates. Then drop duplicates is what you use to remove duplicate rows, right? Then you can use rename to rename columns, to have more meaningful names. So this on the right here, you see some sample code, right? So if you loaded a data frame, you can load it from a CSV file. Most of the time you load it from a CSV file. Then you can do fill now to fill. So for example, this age field, right? You can say, okay, let's use median to fill where the age is missing. Again, this is not just something you do in every case. You have to decide, okay, for this particular purpose, it makes sense for me to use the median age or the average age. Median is a kind of average. There are 3 or 4 kinds of average, right? You have mean, median, mode. So those are different kinds of average. You decide, okay, let's use the median age rather than putting 0, which will not make much sense. Then you have, drop duplicates, which allows you to drop. And then you can also fix inconsistent text. So we're going to do a bit of hands-on session, and I'm just going to go straight to this Jupyter notebook. So the first thing I want to do is I'll just easily go to Kaggle, right? And search for, let's go to Kaggle, kaggle.com. So you go to kaggle.com. In kaggle.com, you can search for data sets. Or first of all, just go to the data sets, right? You see a whole lot of different data sets. You can create your own, right? Now here in datasets, I'm going to search for data pre-processing. So I'll get a few data sets here that maybe contain data that is not very clean. We have this Titanic data for data pre-processing and all of that. So let's start with this one. I'll open it in a separate tab. So normally Kaggle allows you to have a preview of the data, right? So this one is a CSV file, it's 56 kilobytes. And you can see, so one of the things you see is that you have some columns that are missing. So like this one has age, right? But you have some values. This one is missing, right? This one is missing, you know. So you can see all of this. Most of them, the age column is missing. So what I'll do, we could actually have run this in a Kaggle notebook, right? But I want to use I still want to use Colab. So because I want to use Colab, I will download this data set and then re-upload it in my Colab, right? Well, the other thing is you can also use this code if you are using Kaggle. What I would like to try is to see if Kaggle Hub exists in Jupyter Notebook on Colab. If it does, then I don't need to download and re-upload. I can just run this code. So let me do one thing first. Let me just import Kaggle Hub here. Okay. So I'm just running this. It's going to connect, it's trying to connect to an instance of compute, right? So that it will be it will run. So it's looking for a runtime, basically. So if you were searching, you would see it. All right, so I ran this and I got a check, meaning that Kaggle Hub exists in Colab, so I don't need to download and re-upload. And this is very nice for me because it means it will speed things up. So let me rename this and call it data pre-processing. So I have this now. Okay, so now I'll go here. So this is how I can get this version. So I'm just going to copy this code. I'm not going to spend a lot of time trying to do that. They've given us that. So the way you do it is you import Kaggle Hub. I will even go to extent of saying, okay, as KH, just so KH dot dataset download. So I specify this dataset. This is the name of dataset that contains Titanic. It's namespaced. This is the owner of the dataset, and this is the name of the dataset. So I just get the path. Let me see if this works, right? I click on print. So it's going to download it already. So you can already see the code is running, is downloading that dataset, and it has cached it somewhere. So this is the path. So now this data set, I need to check first of all whether it's a CSV file. Let me see. So one way I can easily check if it's a CSV file is I'll add a new code block and I'll load it. So I can now say import pandas. Yes. So I import pandas, right? And pandas is I don't know where I got this from, right? So the interesting thing is my Copilot is telling me I should load this. So I'm going to just run it, right? Yeah, I didn't expect that. So it is the path itself which contains the file. So I will run this. Is a directory error. So the path is actually a directory, meaning that there may be data sets in it. I don't know, but let's check. In Colab, if you click on this, typically I should be able to see my files here. Okay, click on the folder tab. All right. Let me see. Okay, this is default stuff that so let's do something. I want to look at what is in this because it says it is a directory, so I cannot just open it. So I can write some code here. So let me write this code to ls that directory, right? To ls that directory. It says it cannot access okay so I can't do it from the command line. That ls is doing it from the command line, so I have to do it from within Python, right? So to list in Python, will not use ls. I'll just use the OS. OS is the Python library that allows you to interact with the operating system. That's why it's called OS. So one of the things you will do is you can, you know, access files, you can view folders and all of that. So I want to just see what is in there. So I'll do os.list dir and I'll specify path. Okay, so let me just see what's inside there. So you can see I've listed the dir. So what I have is Titanic underscore data.csv. So this is the actual file inside the path. So there's only one file inside it. So to go back to what this, we're supposed to append the name, which is Titanic underscore CSV dot, sorry, underscore, let me see. It's Titanic underscore data dot CSV. Titanic underscore data dot CSV. So this is a file. So I'm going to run this. By the way, let me move all my imports up so that I don't keep repeating the imports. It's not really a good idea. When you are running with um, with Jupyter Notebook, it's always a good idea to separate imports and keep them up there. I already did this, so that's okay. I'll now add a new code block and I'll paste this so it will download and give me the path. Okay. Then this third one, I will now use it. So I'm going to run this code. df is pd.read CSV. So df is a data frame. Remember, PD is pandas. I have imported pandas as PD. So anytime you see me use PD, I'm using a function inside pandas. And anytime I'm using KH, I am I'm using a function inside Cargo Hub. All right, so here I had already used the dataset download function in Cargo Hub to download this data as given to me from Cargo. Now, I use read CSV. So this is Titanic data. I need to figure out whether I need to put a slash here or not, but I will not put a slash yet. Let me just try it. So I run this. Okay, so it says file not found. So let's assume that there is no slash. So I have to put a slash here. And good. So voila, it gives me this, which is the data that is in that data frame. Okay. So um I'm going to, so if you look at this screen is pretty small, so I want to go to a bigger screen. So give me a second. I'm going to switch to a bigger screen. Okay. So I hope my screen is visible now. Um, I'm looking for more screen real estate so we can see more stuff. All right. Okay, so you can see the data now. The interesting thing is if you're using Google Colab, one of the things I love Google Colab is it gives me this additional stuff. So I can actually look at the data, you know, in this format, right? Or I can look at charts, for that data, which is interesting. Anyway, yeah. So a lot of charts have been plotted, but let's run this again. So this is the data. This is head, the df.head. So when you load this, you load into what we call a data frame. Data frame df just is a variable name, right? You can use anything, but typically we use df. So df allows holds the data frame and all the content. Head is a function of the pandas data frame that allows you to see the first few rows in that data frame. So you can see that we are not seeing a lot. We are just seeing some stuff here. I don't need this anymore because I have basically solved the problem I wanted to. I wanted to see what is in that folder, but I'm just going to, keep it here so I don't lose that. I don't really need this, but okay, yeah. So let me put it here as part of this, right? Then I can move this up here as well. Okay, and then I can delete this. Okay, so now I want to do some things. So df dot if we want to view, so remember some of the commands that I gave that you can use. You can get all of if you want to know the columns that have no entry in them, you can use NA. So let's just print out the whole data frame. Let me just do df, right? So it's not giving us the whole data frame anyway, but it's giving us the head and the tail, and then dots in between. Now, if we want to find the ones that do not have anything in them, right? So there is pandas dot is is right. So it's normally a mask that tells us whether you have a null value. So if you look at this one has true here, this one has true, this one has true. Before then, if you look at this one that has true deck corresponds to none. None means not a number. So it means that it is empty. Basically, there is no value in that particular cell. These three don't have values. That's why is null is now giving us true for those three. And then the last as well. So let me do this and just print the whole data frame. If I print the whole data frame, you also see these last three are also nones. So that's why here, the last three also have true, as is known. So a way to filter, to look at all the rows or columns, maybe a column, let's say a column like deck, right? I want to see all of the ones that are null. I could do something like this. df deck, right? Then we use a filter for it. Yes, a mask. So this is what we call a mask. So df deck is null. is this function I just did here. So df deck is null is going to give me only the column that is null. Um, df df deck dot is null. So this will give me just a column, and it will give me true where it is null and false where it is not. Then when I put that, it will give me just those ones that are nans. And, you know, I could also just do this, right? Instead of giving me the whole column, it will give me the entire data frame, but only the ones that deck is null. So this is how you can find some of them that are null. Now, because of time constraint, this class is not really about pandas or data cleaning with pandas. So we have a separate class for that. For those who have done that class, they probably are very happy that they did that class. But some of the things you will do now is for this deck, you could say, okay, I want to remove the ones that don't have any value for deck. So to do that, you would use df.dropNar. If you do df.dropNar, basically it's going to drop every row that has no, whether it is in the deck or elsewhere. So you can see that na that we have here is gone, right? So that's one way. So in this case, I just dropped all the rows that didn't have any values. If you look at this, initially we had 889 rows and 15 columns. By the time we dropped all the ones that didn't have any values in them, we are down to 182 rows and 15 columns. So this is one of the ways that you can do filtering or cleaning of data. The other thing you could do is filter. So filter would be, instead of me dropping these rows that don't have any data in them, I want to fill it with a value. So let's say if I don't have a deck, because this is Titanic, right? So we are saying, okay, if someone doesn't have a deck, let's assume the person is on the lowest deck, and the lowest deck, maybe let's say deck Z. So I can now say df.filter, right? So in filter, you have to specify the value that you fill. Now we need to be very careful. If I do filter Z, that means anywhere you have this empty, it will fill it with Z, right? But not only in the deck column, it will fill everywhere else. So if I want to fill only in the deck column, I have to scope it to just the deck. So I have to say df deck, right? Sorry, this is drop now. Filter is what I'm looking for. So I would say df deck, right? Fill where, fill where, um, you know, where the deck is null, you fill it. So it's only giving us this. But if I want to change the original data frame, I have to reassign it back to the original data frame. Okay. So with this, I would have cleaned it up. If I now go to df, I print the data frame again. After modifying it, you now see that the deck, all the places that had nans, I now replace it with Z values. So this is just examples. It is an entire thing. So drop duplicates is another way. Duplicate allows you, by the way, I have modified my data frame here, which I typically don't like to do that, but that's okay. If you do df.duplicates, it will show you all the duplicates in the data frame. Sorry, it should be duplicated. So, yeah, so it gives you where you have duplicates. Um, let me reload the original data frame because I may have changed some things. So let me just reload before I do that duplicated, so we see what we are getting. So I reload and then duplicated. So it gives me indexes of which rows have duplicates. So anyone that is false means it doesn't have duplicate. Anyone that is true. So row 884 is duplicated. Of course, I will not know which row it has duplicate of. There has to be another row that also has duplicate. If I wanted to print those ones, I would just do something like this. Show me the ones that are duplicated. It actually gives you an index. So with this, I can now find all the rows that are duplicated, and you see some of the things that are duplicated among them, maybe the town, and all of that, additional information. So these are some of the ways that you can do data preprocessing. Now, for lack of time, I want to move on to the next bit, which is model training. So once again, I'm going to move to the other screen so we can view it. So give me a second. Okay, so to continue, now let's do a little bit of training, right? So let's talk about training a model. So what I just did was give you a kind of quick overview of how you can use pandas just to do data cleaning, right? I will give you links. I'll actually give you a material you can go through to understand pandas data cleaning. So do that as your take home. Go and study that material. Try the sample code. I actually have a better notebook, which I'll share with you as well, so that you can use that to learn and try your hands on data cleaning with pandas. Now, for training of models, right? There are 5 stages, which is very, very important for us to understand. And I'm going to do that when I do linear regression with a single variable, right? But the most important thing you need to understand is that you are going to give this model data, then you are going to give it's going to run that data. It's going to do what we call forward propagation or inference. Forward propagation or inference is where the model will give you an answer. It will calculate and make a prediction based on the data. You will then take that inference that the model has calculated for you and compare it with what you are expecting, the actual data, what the model is supposed to give you, right? And then you will calculate a difference, an error, what we call loss. Those are 3 steps. So let me go through the slide. The fundamental goal of training is to adjust the model's internal parameters. Those internal parameters are called weights, biases, there are different names, but the general name of it is parameters. So those internal parameters are what determines the knowledge that the model has. So those internal parameters, you would adjust them so that it will map any input data that you pass into the model. It will map it to a desired output that you want the model to predict. Then, if the model does not give you exactly that desired output, you will adjust the weights. And it is an iterative and continuous process. You keep doing it over and over again, over a lot of data until the model gets it right. By the time the model has gotten it right, you have trained the model. That's the basic mechanism. Number one is iterative. Number two, you give it inputs. Number three, you give it output that you want it to predict. Number four, if it does not give you the output that you want, you adjust the parameters, the internal parameters in the model. So now we are going to look at what do we mean when we say internal parameter? What is this thing self, right? So let's go through the 5 steps. One, data input. The model is fed a large data set known as the training data, which normally should include examples of inputs and the corresponding correct output, right? Then you do what we call forward propagation. In the forward propagation phase, you send the data, the input data, into the model. The model calculates an output and gives you the output. That is the forward propagation. And that output it calculates based on the current state of its parameter, the current value of the parameter. Okay. Now, after that, you do what we call the loss calculation. The loss calculation is where you calculate the difference between what you want it to predict or the desired output with what it is actually predicting, which is the predicted output, right? So that difference is calculated based on something we call a loss function, right? And that difference is what we call an error, right? Now, that loss function will calculate the discrepancy between the predicted and actual values. If you have a high loss, that means you have a high error. That means the model is performing poorly. So it's not giving you very close to what you want. If you have a low loss, it means the model is performing well because it's very close to what you want. The loss is basically a measure of the difference between what you want and what the model is giving you, right? So when you calculate that loss, the next thing you do is what we call a backward propagation, backprop. You hear backprop, backprop. That backward propagation is the most important step. Is the most important step in training because that is where the training actually happens. The backward propagation is the point where you take that error or loss, right? And you now determine how much you should adjust each of the parameters. How much you should adjust each of the parameters until you get the outcome. But the how much is a single iteration backwards. So the single iteration backwards is I calculate for this weight, this is how much I need to adjust so that it give me what I want. For the other weights, this is how much I need to adjust so it gives me what I want, right? And then you propagate this error signal back through the network layer to calculate the gradient. The gradient is a measure of the magnitude and direction of the change that you need to apply to each parameter. The magnitude and direction of the change. Direction means should it be positive or negative? Should you be reducing it or should you be increasing it? That's what direction means. Magnitude is how much, by how much should you reduce or increase the weight or bias or whatever the parameter is. Should I increase it or should I reduce it? That's what we mean by direction and magnitude. Once you have calculated that, then we will use what we call an optimization algorithm, which is an optimizer. So when you hear optimizer, right, that's step 5. The parameter optimization is when you now say, how much should I increase, right? So there are different algorithms for it. We have gradient descent. We talked about that. We talked about things like stochastic gradient descent, Adam, extended Adam, and so on. So it uses the information in the gradient to actually adjust the parameters. So you don't directly apply the gradient to the parameters. You don't directly apply the gradient to the parameters. You use some, because if you apply immediately, you could have the the model will just blow up. It will not learn anything. So some of the things that you do when you apply the gradient, you can use what we call learning rate and all of that. So at the end of the day, when you adjust these parameters, the parameter comes closer because you have, it's an optimization problem. You want to reduce the error. So by the time you adjust the parameters based on the component of the gradient, right? Or the total loss, the component of total loss, which we call the gradient for each parameter, it will now get to a point where the predicted value comes closer to the expected value or the desired value, right? You do that over time, continuously, iteratively, multiple times, multiple times. That is when you say the model is learning. Why is the model learning? Because you are adjusting the parameters, it's coming closer and closer to what you want it to predict. It's getting better and better at it. That is learning. So when you finish, remember you are going to do this over a lot of iterations, sometimes tens, hundreds of thousands, sometimes millions, sometimes even billions, right, of times. But for small models that we'll be doing just a few millions or maybe a few hundreds of thousands. Is what we call epoch, right? At the end of the day, when you've done all of that, the outcome is that one, you have a model that has learned because the final result is a trained model. The parameters inside the model are optimized. They end up representing the pattern that you want it to learn, right? The patterns and relationships in the training data. That's number one. Number two, that model is able to generalize because you have trained it on a lot of data. It has seen a lot of data. It's learned how to predict the patterns in that data by adjusting it. It has generalized its learning. So what it means is that if you give it new data that was not in its training data that it has never seen before, it can make a prediction that is close and accurate because there is some form of correlation in the data itself. And that's why if you cannot train a model to predict data that has no correlation. If you take random data as input that has output that is random, you train a model, it will never get it because it will learn a pattern, but that pattern is not the real pattern. It's random, right? So what this means is that any data you want a model to learn, there has to be some kind of pattern in it, right? It will learn to see that pattern. It will learn to extract that pattern. So when you give it new data, that new data somehow sees that pattern. So it is going to be able to predict and give you an outcome or a prediction that will be close to what you want. That's what we call generalization. Generalization is basically the ability of a model to be able to predict an outcome that is accurate or close to accuracy on data that it has never seen before. That's why it's generalization, because if it's data it has seen before, that's memorization or overfitting. Then evaluation and testing, that's the third thing. You'll be able to evaluate that model. You'll be able to test it on different other data sets, what we call a validation data set or a test data set. And you ensure that it performs very well in real world scenarios, right? I wasn't just memorizing training data, because if it does not give you a good prediction on test data, that means it was just memorizing. And therefore, it's not a true model, right? So this is an example. If you see this is what we call cost function, right? A cost function is normally a quadratic value that you can minimize. So we'll talk about that. So now I have about 20 minutes. I'm going to talk about the mathematics now. So I hope those who I'm seeing a lot of comments here, and I hope people will not run away. So let's see how we can understand these concepts using very simple principle. So what is linear regression? Linear regression is a statistical method that uses a straight line to model relationship between various data. Okay? Between dependent variable and an independent variable. Okay? So if you look at this equation here, you have y equals mx plus c. This is a standard equation of a straight line, right? Where y is the value on the y-axis. M is what we call the slope, right? Or gradient of that straight line. X is the independent variable X, which Y is independent is its value can change. It does not depend on anything, but Y depends on X. That's why it's called a dependent variable. Then C is what we call the constant, right? So this is a number that when X is 0, that is the value that Y will have. So Y doesn't always start with a 0 value. Y can start with a non-zero value, which could be either positive or negative, right? So this is the equation for a straight line, what we call a linear equation. And that's why we're calling it a linear regression, because we're doing a regression using a linear equation. Now, what is regression? What is regression? Regression is prediction, basically, like we've said before, right? So you use linear regression to understand how changes in the independent variable, which is the X, is associated with changes in the dependent variable, right? To predict a future outcome. Okay. It's a fundamental building block of machine learning. So a model that finds a best fitting line through data points, using mathematical reasoning. So in this case, we are using mathematics. That's why it's called mathematical reasoning. We're using mathematics to do the prediction or regression. But as a matter of fact, everything that we do in machine learning uses mathematics. Otherwise, computers will not be able to do it, right? Because computers are basically mathematical machine. So given a few data points, right, find the best fit line. That's linear regression. So let's look at the maths of it, right? And I'm going to quickly run through this because I need to write code and I need to show everyone how it looks like, right? So the goal is that for you to find a line of best fit, typically the thing is that you are given various data points. The line of best fit is the line that has a least, let me use the least error. I wanted to qualify error with something, but let me just say the least error, right? But the error is not the error of a single thing. It's the error of the multiple data points, okay? So for you to measure the error, and so here is where I want to pull up and do some bit of sketching, right? So if you let me see if I have um okay, I'm going to do this because I do not have let's do this. So let me explain when we say least error, because we need to be able to understand what's happening. I'm going to pull up uh, something I like using for sketching. It's a very nice tool. It's called Draw, right? I can use it to draw stuff. So I have a whiteboard here. And I'm just going to swing to somewhere here. Now, this is what I'm saying. I want to draw, let's say I have 5 data points, X and Y values. So I'm just going to use pencil. So I have X and Y values. Okay, so I have X. It's too thick. Okay. So I hope you can see my screen. So I have X values, right? The X value I have an X value here. Um, or let's say XY values, right? X and Y. So I have X and I have Y. And the X is let's say 3 and 5. X is 3, Y is 5. That's one value. That's one data point. I have 4 and 8. Okay. And then I have 10 and 2. I'm just randomly generating numbers. So I didn't plan this at all. 8 and 9. Okay. But I'll try to get these numbers around the same area. 5 and 10. So I have 6 data points. And maybe let's say 6 and 9. So I have 6 data points. If I draw this as a graph, I will have the y here. So, and I'll have the x here. Now, if I want to plot this, so let's just make this very simple. This is halfway, this is 5 on the x, and this is 10. And then on the y, the highest y value I have is 10 as well. So I also have 5 here, and I have 10. Now I want to plot. So the first point, 3 and 5. So this is about, okay, 5, 2.5, 1, 2, 3. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we also have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 3 and 5 is here. That's the first point. Then 4 and 8 is somewhere here. Then, okay, let me use a different color for this. So let's say blue. So 3 and 5 is here. Oh, sorry. 3 and 5. This is 3 and this is 5. So this is 3 and 5. This is 4 and this is 8. So this is 4 and 8. This is 10 and 2. So this is 10 and this is 2. 8 and 9. This is 8. 5 and 10. This is 5 and this is 10. 6 and 9. This is 6 and this is 9. So if you look at this, right, we do have one funny outlier here. Maybe let me change this outlier just for the sake of it. 10 and 2. It reverses everything. So let me flip it to 2 and 10 so that so I'm going to flip it to 2 and 10, right? So this is 2 and this is 10. Now, so I'll plot that one as well. So this is 2 and this is 10. It's still funny. So if you were asked to draw a line of best fit, so I have to take this one out. If you were asked to draw a line of best fit, maybe use your eye, right? Let's just draw a line. Okay, so I use my eye and draw a line. So the line will look like this. Okay. Now I've drawn a line. Now the error, okay, I'll draw 2 lines. So I'll draw that line and then I'll draw a line that is really bad. So let's look at this line here. So I draw 2 lines. If I want to calculate the error, so remember we are trying to train a model to fit this line. So what we will do is we will, let me use a different color. Let me use green. Now, to calculate the error, what you do is on this line, this is the prediction. So on this line, for this one that is 2, sorry, this one that is 3, 5. This line is predicting, instead of predicting 5, it's predicting maybe 8. So you now have, I hope you can understand that 3 and 8. That's what this one is predicting. Then when it is 4, is close, is actually close. So this one is predicting 4 and, oh, okay. So this should be 3 and 7, 4 and 8. Let me just, 3 and 7, right? 4 and 8. Okay. While that's when this is 3. Maybe I need to use lines. So, but I think you get the general idea. The idea is that this orange line is predicting on its own line, right? So when it is 5, when it is 2, orange line is predicting 7. It's actually 7.5, you know. So the bottom line is this. For the orange line, right? This is the error. The error is the distance between the y value of what what it should predict here, right? Minus what is actually predicting. That is the error. In this case, the error is positive because it is higher. In this case, the error is negative because it is lower, right? And here the error is almost 0 because it is close. Here the error is positive again. Here the error is negative. Here the error is negative. So if you sum up all this error, that is a measure of the total error that this line, is making in predicting these blue dots, right? But because of the positive negative, we don't want to, the positive negative is going to basically cancel out. We don't want to cancel out, right? Rather, we want the positive negative to add up. So that's why we have what we call mean absolute error and mean square error. In the case of mean absolute error, in the case of mean absolute error, we will take absolute values of this. But in the case of mean square error, we'll take relative values. Let me take this thing now, right, and put it in a Jupyter notebook so that you will see the actual calculation. I can plot this with Matplotlib and we'll see how it goes. So that's the first step. The first step is we do the prediction, right? And we find that there are errors. Then the next step is how do we propagate this error back? Okay, so give me a second. I'm going to do this on screen right away. And someone is asking, how do you know what it should predict? You already have the data. What it should predict, that's what we call labeling. You are labeling the data. You're essentially telling it what it's supposed to predict. So I'm going to start 3, 5, 4, 8, 2, 10, 8, 9, 5, 10, 6, 9. Let me pull this out so I can easily type it in. So this is the data, right? So you can put it this way, X and Y. That's the data that we want to predict. Okay, so X, or we could just say data. Now I can make it a list of lists. So 3 and 5, right? If you remember, then 4 and 8, 8. Okay. Then 8 and 9. Okay, I missed the third one. 2 and 10. So 4 and 8, 2 and 10. Then 8 and 9. Then 5 and 10. Then 6 and 9. Right? 6 and 9. So this is the data that I want to predict, right? The data that you have is in pairs of X and Y. Now, if I want to get the X values and the Y values, I can easily use what we call zip. So I'm going to do X comma Y equals zip of. So I can now, let's see what X and Y look like. Okay. I have to spread it out. Sorry, zip. Okay, this is an array, so singles, right? Okay, so X is now 3, 4, 2, 8, 5, 6. Those are the X values. And then the Y values are 5, 8, 10, 9, 10, 9. 5, 8, 10, 9, 10, 9. So this is what you wanted to predict. You ask, basically, I'm now telling it, if I give you 3, I want you to predict 5 for Y. If I give you 3 for X, I want you to predict 5 for Y. If I give you 4, I want you to predict 8 for Y. If I give you 2, I want you to predict 10. If I give you 8, I want you to predict 9. If I give you 5, I want you to predict 10. If I give you 6, I want you to predict 9. You have given it the value. So to now plot this, right? Right? Plot X and Y on a scatter graph. You can use a matplotlib to do this, right? So if you look at this, it does this already. So you can already see, let me move this up so we can see more space. Yep. All right. So I hope this is going to be, I need a bigger, so you can see this is now a cleaner plot, right? I was drawing it by myself and it wasn't looking too clean, right? But Matplotlib has now, you know, done a better job for me. So this is my own sketch, right? And this is, you know, this is a sketch from Matplotlib. So it sketches that. Now, so I wanted to do this prediction, but it's going to use a linear equation to fit this. So we will start off with so we'll start off with, let's go start off with the y equals mx plus c. Now we will calculate the error. This is a function for calculating the error. If you look at this function, there's a lot of mathematical symbols here. And everybody will be scared by this. But let me tell you that this is a very simple thing. Remember, I said mx plus c is the prediction. So let's assume I have a function, right? Let's assume I have a function. This is how we do the training. You start off by saying, okay, y equals m times x plus c, okay? This is our function. And I'm now going to make it a function in Python. In Python, you make a function by defining it, right? So we'll define y. Let me just define it as y pred. Y pred x is this function that I have put here. So this is very simple, right? So we can now return y, right, as a y pred. I can use underscore or something. But y pred is the predicted value. It's not the actual y. That's why we need to differentiate. Sometimes we call it y hat, okay? So sometimes predicted y is called y hat, right? Y underscore hat. Or y, it has this, there's this y here, which I don't know if I can get it out from here, right? This, see this y here that has a little caret on top. That's y hat. Okay, so now the only thing is that I don't have M and I don't have C. These M and C are properties of the prediction. So are properties of the model. Okay, I don't know how to represent this because this is a function, but let's give it values. So let's say we start with M being 1 and C being 2. So remember, one thing that most people don't realize when you are creating a neural network, or in fact any model, I go to neural network because that's my reference, but any model, you always start with a random value for the parameters. In this case, we have two parameters, the M, which is the gradient, right? Or slope, and C, which is a constant. And I just started with any value here, 1 and 2. So with this now, I can predict. If I now go to plot scatter, so I can also do a plot dot line. And instead of using Y, I plot X, which is still the value I want to plot for each. But I now plot what I am predicting. With this, I'm now predicting it will use a different color, but I'm plotting a line, because when you are predicting, that's the whole essence of generalization. The whole essence of generalization, I need to create this first. The whole essence of generalization is that I should be, so I need to add stuff to this, right? So, marker is non-line. You have line style. Okay. Color is red. Okay. So, yeah. So this will now do what I was trying to do. I only concatenate tuple. Where am I trying to concatenate? Oh yeah, okay. Yeah, because I'm using tuples. So I'm going to change this to NumPy stuff. Okay, let's do it this way. I have to use a loop. Let me use a loop. So for yeah,
So the predicted, is it taking a list?
yeah, it's a list.
Okay, X is a
So
list.
that's why it's a problem.
But
I
is
could
it
convert
returning a
it to
list?
NumPy. Yeah, it should
Is the
return a
Y
list as
returning a
well.
list?
It should return a list. So let's
Okay.
just do this. It should be a list or a tuple, right? So it should be a list. So
Ta ni NumPy ló máa jẹ́ list o.
I dot append.
Tó bá append lókun.
Okay, so right. So Python people understand this. I'm basically doing it manually. I'm not going into NumPy yet, right? So I'm basically like this X that is coming in is actually a list. It's a list, right? So that's why it was failing. It was failing because I was trying to calculate I was trying to do mathematics with a list, which is not possible. I need to convert it to a NumPy ND array. I'll do that later on, right? But I was trying to do mathematics with a list, so it didn't allow me. So now instead of that, I have to go through each of the I don't even know why I'm doing range of length of X and all of this. Instead of for you know, why couldn't I just do for xi for xi in X and I just do xi, which is really the correct thing to do, right? So this is the correct thing. So this now, I'm now basically looping, or even better, I use list comprehension.
That's return,
Return.
yeah. Return list
Let's use
comprehension.
comprehension. Xi m times xi plus c for xi in X. So this is what it should be. It's just simple list comprehension. I don't need this anymore. I can even do this MC. So we see it as real parameters, 1, 2. So I'm now fine tuning the code that AI gave me, which is why it's good for you to be smarter than AI, right? So this is the code. So I can run this now. Okay, so it's giving me I need blocked lines, so it shouldn't be scattered. plot. Let's just do plot, right? So it will give me an actual plot instead of a scatter diagram. Color is red. Red. Can just do red. I think it knows red this way, even though probably quotes, putting in quotes is better. Okay, so right now, so we run this. Okay, so we now have a line, right? But this line is not a line of best fit. Okay, it's not a line of best fit. So I'm going to do linear regression by hand with the help of this thing. So this is with this parameter of M is 1 and C is 2. Okay, I get this line. Basically, I'm able to plot it, right? While this is the data. Now, I need to calculate the error. So one thing I would even like to do is to add the error, right? Okay, so display the error in the plots. So I'll do I'll come to that, but let me first of all calculate the error. So to calculate the error, okay, this formula that looks very complex, let me break it down. First of all, the first part of this formula is going to tell us the predicted value, mx plus c. That is what I just did in this function, right? That's what I just did here. Mx plus c. That's y pred. That's the predicted value. So what we actually have here is y pred. Okay, this is y pred. Maybe I should, use a red color. But this is y pred. This is a predicted value right here. So we are just trying to calculate the difference between yi, which is the yi is what? The actual value I want it to predict, right? This is yi. I want it to predict this value for me. So it is blue. This is what I want it to predict. Okay, but it's not predicting. This is the actual value, right? This is the label value. This is what I want it to predict. That's yi. This is what is actually predicting. So by subtracting it, I'm getting what? The error. Okay, so this is it's the maths. The thing with maths, one thing I figured out with maths is the problem with maths. Maths is not hard. Is the symbol. The symbols are too math symbols. I don't even understand. Like they write all these things. I don't know what it means. Maths is a language. So most people have problem understanding the programming language of maths, which is just the symbols, right? So in this case, we have this. This is what I want to predict. Now, this is what I'm actually predicting. So that difference is the error, but I have to square the error. I have to square it. Why do I have to square it? Who can tell me? Why do I have to square this error? Why do I have to square it? Because if I don't square
So
it,
that's
the
so
negative
fancy.
values will cancel out the positive values. I hope that's what if we wanted to say. The negative values will cancel out. I don't want the negative values of the error to cancel out the positive values. I want them to remain because I want the cumulative error. I want the total error. So I square it. So that's two things. And that's why it's called mean square error, right? First of all, you square the error. In other words, the error is yi minus y hat. Y hat is mxi plus c, which is the predicted value. I square it. Then when I square it, I do this thing. This thing is a summation, is the sigma. That's the Greek alphabet. That means summation. It means I want to add it. I want to add the total squared error of each error. I want to add the total of each squared error, right? So I get that total. I equals 1 to n means there are n data points. I have added n total square. together. So I have what we call sum of squares. Sum of squares, or what you call squared error. That's a squared error, SE. The sum of the squares of the error. Then I divide it by n. I divide it by the total number of elements. Whenever you divide a sum of something by the number of things that were there, what do you get? Is the average, the mean. So that's why it's called the mean squared error, because it is the mean of the sum of the squares of the error of each data point away from the prediction. That is this whole thing. That is J. J stands for cost function. So that's the cost function. So this math, when you now see this formula, it will now confuse you. You say, man, what does this thing mean? It is not magic. It is not hard. It is simple. This is the mean square error. That is the sum of the squares of the average, or which is average is sum over n. So the average of the sum, well, average is sum divided by number. So it's the sum of the squares of the difference between what I want to predict, what I want the model to predict, and what the model actually predicts. All of that divided by n, that is a mean squared error. That is what this formula is, and that's what MSE means. So now, the interesting thing is this. MSE, the cost function, is quadratic. So now this can get confusing because you can begin to think, oh, this thing is quadratic. This is the actual function I'm trying to approximate or trying to predict. No, this is not a function. This is a plot of the error function. And the reason why it's quadratic is because it's square. Remember, a quadratic equation is x squared plus 2x plus 1. That's an example. Ax squared plus bx plus c. A quadratic equation always has this shape. So any function that is squared always has this shape. It's either this or reverse upside down like this. But in the case of a cost function, it will be this way because it's going to have a minimum value. Do you know why it's going to be a minimum value? There are certain values of this y, because you are squaring it, when it is too large, it will go up. So there's a certain point here, a certain value of m or c that you will pick, that will reduce this to the minimum. It will never be zero because the error, there will always be a little error, right? So it will never be zero, but it will be able to get as close to zero as possible. That's what this line means. So if you are at a very high point here, right, for m or c, this value of error will be very high. If you're also at a very low point here of m or c, this value will also be very high, but there will be a certain value of m and a certain value of c that will give us very low this thing. But the thing is this, the effect of m on the error is independent of the effect of c on the error. You can plot them separately. So what we do first of all, we can plot this, right? Cost function. So let's go and look at it. So I want to now, okay, so let me do this in the next line. Let me close this up a bit. Right? On this next line, you can now have a function called cost function. And this cost function is still x and y. So cost function has to be x and y because you are comparing predicted versus actual. Now, I could do all of this. This is basically the function because you are doing sum. You are doing mx plus c, right? Mx plus c is the predicted value, right? Minus yi. Yi is the actual value. So while in this place, we are doing it the other way, yi minus mx plus c. But here we are doing mx plus c minus yi, right? It's the same thing because you are squaring it. So the sign will go away. So you square it. This star 2 will square it. So for xi, yi, and zip xy, so this is basically just doing all of that. And then it's dividing it by the number of x. this is difficult to see. So let's do it step by step. I'm going to start by first of all saying the error of each one is y. So let's say, let me do sum. We know we have to sum it, right? Okay. Then for xi in x, or you have to do a zip. So for xi comma yi in zip of x comma y. So you zip those two. Zip is a very powerful, handy thing in Python that allows you to join things together and separate them. You know, like your zipper. Now, when you are zipping your clothes, what are you doing? When you pull it up, you are zipping. You are joining two parts of your clothes together. When you unzip it, you are separating two parts of. That's what zip. That's why it's called zip. You're basically zipping x and y. You know, changing its data structure. So this zip. Let me show you what it looks like so that you will not be confused. If I do x and y, right, and print it, you are just going to see two separate sets. X on its own, 3, 4, 2, 8, 5, 6. Y on its own, right? But if I now zip the x and y, you see that zipper action, you will see it. It's actually going to zip the two. So you're now going to have, okay, I need to turn it into a list so that you can see it. So let me turn it into a list. Okay. So you now see it has now zipped the x and the y. So x that was 3, 4, 2, 8. Let me do it. You know, let's print it so you can see print x, the tuple of x and y. Then we'll print the zipped, right? We can make this a tuple so that it's also a tuple so we can see it. Now, when you run this, see the difference. 3, the zip is that I've taken this 3 here and I zip with 5. That's how a zip behaves. I take the 4 and I zip with 8. So we have 3, 5, 4, 8, 2, 10, you know, 8, 9, 5, 10, 6, 9. So 6 zips with 9. So think of it like this one is one side of your zipper. This other one is one side, the other side, and then your zip zips the two of them together. So you now have this. So anyway, so you now have this, right? I now have xi and yi. I now calculate the prediction. So I want to calculate the error. Okay. So I can do the error without a cost function. Let's do step by step how this cost function happens. So I do xi and yi, right? These are just the values. Okay. If I run this print cost function of x and y, right? What you get. Okay, so this is a comprehension. I'm getting tuples, so I should put this thing around it. So this is just giving us the same thing as if it's just giving me the zip back. Okay. Now, so that's the beginning, but I want a single value. So I can do x, I do predict y pred of xi. This is the predicted value of xi. Missing something. Oh, okay. Yeah, right. Okay. So I cannot, this is prediction of multiple. So let me do prediction of single. Pred, y pred of a single value. Let me call it single. So I want to do prediction of a single value. So it should just be mx plus c, m and c. Okay. Right. So y pred single. So right now I'm just predicting only the y value. Okay, so this is a prediction based on this x. So you can see the prediction is 5, 6, 4, 10, 7, 8. Is 5, 6, 4, 10, 7, 8. While the actual value is 5, 8, 10, 9, 10, 9. 5, 8, 10, 9, 10, 9. So if I were to even put them together, well, you would see it. Let me do something. Let me do it this way. Let me print y first. Then I print the prediction so that you can compare. So this is why 5, 8, 10, 9, 10, 9. But this is a prediction 5, 6, 4, 10, 7, 8. So that's why you, if you look at the graphs, which I had shown here, where's the graph? You see it follows. Okay, now I now do calculation of just the differences. So I just subtract minus y. So I'm now subtracting. So this is now the error. This is the individual error in each position. 0, the first one is 0. It's predicting 5 correctly, 8, 10, but the rest, there's a little error, -2, -6, -1, -3, 1. That is the error. Then for me to calculate the sum of the error, if I just did sum of error without squaring it, the total error will be less than the error of one of them. Take note, you have an error as big as -6, but if I sum it, okay, the sum should be outside. The sum should be outside. So I sum the values. Okay, so I sum the values. So you can see the sum is -11. Now, the reason why this is -11 because everything is negative, but that it can cancel out. So we have to square the values before we sum it, right? So to square the value before we sum it, we now do raised to power 2. This squares the value before we sum it. So this is now the sum of squares, 51 of the errors. That's the sum of squares. Then we now divide it by the number of items. So that is length of X or Y. So this gives us 8.5, which is the mean square error. So with this, we have arrived at this function. This function is what we just did. And there are many different ways you can do it. I'm going to share this notebook later on. But now we have a problem. Okay, we have measured the error. The next thing is we want to do the next thing, which is to find the optimal M and C, right? We do this thing we call gradient descent. So the gradient descent is you calculate the gradient of the error with respect to each parameter. So the gradient of the error is how does the error change if I only change M? How does the error change if I only change C? That's it. That's what that is. So you calculate that there's a mathematical equation. If you actually look at the this function and you do, this is where the calculus comes in. If you do calculus of this, right? Right. This is the derivative of this is 2. If you are using with respect to M, it will be 2 times Y minus um, X, right? 2 times yi minus xi. And then if you do it with respect to C, it will be 2 times, yeah, 2 times yi. It's just 2 times yi minus 1, right? So those are the derivatives. And you now plug them in. In other words, those derivatives should give you 0. So you solve it backwards. Because of time, right? I unfortunately cannot go into the mathematical derivation of this gradient. But at the end of the day, this is the formula that you use to calculate M, right? Where this is 0. If you plug it all back in. And this is the formula you use to calculate C. So by the time you take all of this formula, this will tell you the actual M. But the actual M and the actual C is not really what we do in training a model. In training a model, this one is like you are doing mathematical analysis. So you do the mathematics and you solve it immediately. But in a normal situation, this is not what we will do. What we will do is I would need to calculate the gradient of the cost function, right? and then I'll apply that gradient and I'll adjust. So I'm not going to go do all of that calculation, but I'm going to just do the adjustment. So the adjustment part of it is this. If let's say I do the calculation of the gradient and it tells me adjust M by 0.1 and adjust C by 0.1 also. Okay, so if I adjust M by 0.1, maybe increase M by 0.1, this will be 1.1, and increase C by 0.12, this will be 2.1. This is normally how the machine learning algorithm does it. It is not this one that is a mathematical calculation. And maybe I'll run through it again on Thursday because I think I've overshot my time. But yeah, so you now have a new value of M and a new value of C. Here too, you also have a new value of M. Is the same thing, right? So with these new values, if you recalculate, right, you will find that your graph changes. You see, your graph has shifted a little bit up. Before it was here. Maybe what I could do is use the old values and you see, but let's see, right? This is old values, right? If I plot this graph with old values, you see where it is. It is down here. Now, if I change the values to 1.1 and 2.1, take note too, before I run this last one, take note, this line goes straight through this. That's why it got a good score on this first point, and then it goes here. But with this new value, you can see that the line has shifted up a little bit, right? It's getting closer to these other values. So with this now, with this 2.1, I can now calculate the new cost function. If I calculate the new cost function, you see it's 7.39. In other words, the error has reduced from 8 to 7. So that means I should keep adjusting. So I can now use gradient again to adjust. Oh, sorry, I need to also increase it here as well. Okay. Now, yeah, so I'm manually basically, adjusting it manually because I told you I'm going to do it manually. So I now add it, I increase again by 0.4, right? So this is the part where the optimizer does. It is when you are learning, when you are training the model, you are essentially adjusting the parameters. This is the thing I want to really illustrate to everyone so that you understand that this is when we say a machine learning model is learning, what you are basically doing is that you are adjusting these parameters. But now I am adjusting them manually, right? When we are using TensorFlow, PyTorch, and all those things, it is automatic. So now with 1.5, 2.5 as the M and the C, you can now see that this graph has now, it has even crossed to the other side. Interesting thing. That's why we say it's a quadratic curve. On the other side, the error will begin to increase. So let's use that same thing and we'll see here what the error is. You can see the error is now 10.16. It has increased. We got from 8 to 7, then we went up to 10. So we have to go back. So I will now reduce it because it was too high. So I'll now go back to, in fact, what I will do is, in order to speed things up for myself, I'll move M and C outside of this so that we will use a single value for it. So I don't need to keep adjusting in multiple places. So now I'll go back to 1.15 because I went to one, I'll just go back to 1.15, right? So run this one, run this one. You can now see it has come back here down. Let's see what the error is. I'll remove these ones here so that I'll use the 1.15 that I have in the global space. So I'll run this and you see it's 7.11. Okay. Before it was 7.6, now we are 7.1. I'll increase it a little bit more just manually, maybe 1.2. So this is basically manual gradient descent that I am doing. I'm not calculating the gradient though, I'm just guessing it, right? So now it shifts up a little bit. Let's calculate the cost function again. It is now 7.00. It is reducing. I am training this model. It is getting better and better at being able to fit this data. Now, one thing I could do is, okay, the gradient, maybe I should change the gradient a bit. Like let it bend somehow. So I will reduce the gradient and increase the C, right? So let's all just increase the C without reducing the gradient. Go to 2.25. Run this, right? Run this. It goes up a little bit. Let's see what the error is. 6.9. So I'm getting better and better because the error is getting smaller and smaller. Now, if I go to 2.3, without changing the gradient, I'm just changing only this, right? Um, let's see what the graph looks like. Okay, let's see what the cost function looks like. It's 6.8. Let me tweak this a little bit. So let me just guess some kind of values, maybe 2.5 and 1.3, right? So 2.5 was giving me problem before, but that was because I also increased the gradient. Now I'm not increasing the slope, rather. I'm keeping the slope. It's back to 7.3, so it is too much. So this is basically how machine learning goes. It keeps going back and forth and oscillating like that until you arrive at a minimum value. Now, this is a way of guessing, right? And this is really how machine learning algorithms do it, because you cannot do a mathematical for a single a linear regression with a single variable. You can actually do a mathematical calculation and arrive at a value, but with a something more complex like a neural network, you cannot, it's not solvable. So you have to do this process of manually adjusting at well, not manually, automated process of adjusting at a very fast rate, until at this point you can say that these two parameters, m at 1.2 and c at 2.4, come close to the line of best fit. There is this outlier. Maybe there's another value that if it crossed like this, it would have also worked. If M is very low and C is 9. So let me try that. There's another set of values. So this is the old values. Let me try a new set of values with M and C. M being very low, a very low slope, because I want it to be almost flat. And then C being at number very close, number maybe 8.5. Okay, 8.5. This one I'm just visually looking at it. You now see that the graph, you now see that the graph has changed, right? If you can see that. So the graph has changed. It is now almost flat, right? It's almost flat. And you can also see, apart from being almost flat, let's look at the loss. If you look at the loss now, the loss, let's see. You can see we have a loss of 2.9. So yes, now with gradient descent, there would have been a way that we would have basically, you know, gradually adjusted it until we get this value. So you see how much better this is in terms of error and all of that. So this is essentially gradient descent. This is how you train a neural network. So I'm just going to wrap this up um, with, yeah, I'm going to wrap this up now. Okay, so that is basically how um, training neural networks or training any machine learning model generally, that's a general method. So you will find that what I was doing was kind of a gradient descent, slowly adjusting parameters until I get a very low value. So, but linear regression with one variable, in this case, we kind of came out with a mathematical solution that will give us the M and the C in one go, right? But in the real case of it, it is never like that. So this is also if you when you are finished, you can write this kind of code to visualize it, right? And this is a good example of data. The data is the blue one, and the red line is your linear equation, that's line of best fit that will predict it. So that is the end of linear regression. By next week, by next class on Thursday, I'll show you we'll dive a bit more into the gradient function and how you can automate this process. Now I'm doing it manually, but we'll automate the process. Thank you, and I hope we enjoyed the class.